Hello and welcome to my channel. Today I would like to start a really interesting and exciting project. We are going to build small bipedal robot. It's a very complicated project and I think it's going to take more than one video. I think it's going to take 2 or 3 videos. So I would say that there are 3 main parts. First part is the simulation, reinforcement learning training of this robot inside the simulation. For this we are going to use NVIDIA Isaac Sim and NVIDIA Isaac Lab. When this simulation is done, we're going to make the physical robot, the hardware. And afterwards we're going to put this model which we trained in the simulation, we're going to put in the hardware and make the real robot to work. Why we start with the simulation? Because with the simulation we can be sure that at least from theoretical point of view, our robot can work. This project is very complicated, so it's supported by NVIDIA in terms of the simulation. So I'm going to use the help of the NVIDIA. For this I have the graphic card RTX 4080 for training. And I'm going to use NVIDIA Isaac Lab, which is probably the best software for the reinforcement learning for robotics. And from the hardware point of view, I'm going to use the motors from the Actuator company. I have many motors like this, 10 of them, 5 for one leg, 5 for another leg. These are the customized motors, and we make these motors with Actuator company together, specially for this project. And for the brain of this robot, I'm not sure. Either I'm going to use Isaac Jetson AGX Orin, which is definitely enough to run this model. Or maybe I can use the lighter version, Jetson Orin Nano Super. I think I will try with this one. If this one is not powerful enough, I will go with this one. And for the power supply, I'm going to use the batteries from this robot arm. So these batteries. So actually when I built these batteries, I already had the idea that I can use them for the bipedal. And I don't know yet what I'm going to use for the IMU, for the inertia measurement unit. So now let me explain the main concept. I took the inspiration from the Disney bipedal robot, from this one. By the way, you can find the article about this robot on the Disney website. And what is interesting is that this robot is mostly 3D printed and it has quite simple construction. Simple means that the actuator is in the joint, which we can see over here. Like this actuator, this actuator, this one, this one, this one. So there is 5 actuators per leg. Exactly what we are going to use, 5 actuators per leg. There is also second advantage of placing actuator inside the joint. And this second advantage is that in this case it's easier to simulate this robot. Because you just need to simulate the actuator and you don't need to simulate the transmission between this actuator and your joint. It's easier for hardware construction and it's easier for the simulation. And by the way, if we took the G1 Unitary humanoid robot, it also has the actuators inside the joints, in the legs. By the way, over here they use the IMU with a 600 Hz communication rate, which is quite high. I don't know what they are using. Unfortunately, they have not specified the model of the IMU. And the second robot which I used for the inspiration is a Berkeley Humanoid, which you can see over here in this article. This humanoid is more complicated than Disney one, but it also can work. And I really like this table which says which kind of actuators is using in all these different robots. This robot has 6 degrees of freedom per leg, so it has the additional degree of freedom in the feet, for the motion of the feet like this, adduction, abduction. But what is nice is that this Berkeley humanoid robot, it has the open source software, meaning that you can find the reinforcement learning training model on the GitHub. And so this is exactly what I used. The only problem is that this reinforcement learning model, it was written for the older version of the Isaac Lab. And I think it's not a good idea to use this older version, so I decided to rewrite this for the newer version of the Isaac Lab. So to have this reinforcement model for the newer version of the Isaac Lab, and afterwards to modify this version for our robot. And here's the initial sketch of our future bipedal robot. Actually, it's only sketch of the one leg, of the left leg, this one. And as you can see, there is this actuator for the hip rotation, the smaller one. And also we use a smaller actuator at the feet flexion extension. So 3 big actuators and 2 small actuators per leg. This is a model which I used to create the URDF file. The thing is that in our model, the knee can rotate in both directions, which is not like in a human knee, but why not? By the way, if you would like to learn about AI or about simulation for the robotics, like the Isaac Lab, reinforcement learning and stuff like this, now it's the best time. Because on March 17th, so very soon, the GTC conference starts. And on this conference, you can learn about all of this. And the best thing that there you can find the sessions for the beginners and for the professionals. So whatever level you are, you will find something interesting there. And also there are a lot of sessions about humanoids. This is what really interesting for me. Let me show you. It starts on March 17th and it goes up to March 21st. It's absolutely free if you attend this conference virtually. This is what I'm going to do. So the keynote is going to be on March 18, and it's over here if you want to visit in person. And look at these talks, like the rise of humanoids, AI for humanoid robots. I think this one would be super interesting for all my viewers. Accelerating robust humanoid robot development for any industry. Bridging sim to reality. Perfect. Many of these talks is exactly what I need. 1,212 sessions. And as you can see, there is a different technical level, beginner, intermediate, advanced. The keynote is going to be on March 18th. Also, what is interesting for me is that there are some sessions about startups, like insights and strategies for scaling your startup. I visit this conference every time for already maybe 3 or 4 years. And I think it's super interesting and I always learn something new there. And all of this for free. Now let's briefly talk about these actuators. As I told you, these are customized actuators, but they are based on the standard actuators. So the small actuator is based on this X825 actuator from my actuator company. And this actuator has 25 Newton meters peak torque. I suppose our customized version also has around 25 Newton meter peak torque, but it's customized for the higher speed, for the higher rated speed. So over here, its standard model has 110 RPM. I suppose that our customized version has around 200 RPM. And for the big actuator, it's based on the X1040 actuator. So it's bigger, it has 122 millimeters in diameter. It has a gear ratio of 7. Peak torque 40 Newton meters, and again the RPM is increased. It's more than 200 RPM, and the weight is 1.1 kilogram. I'm not yet sure what I'm going to use for the IMU, because this IMU should be fast enough. I know that Berkeley robot use this IMU, ICM 42688. I think they use some standard PCB with this chip and with some electronics, I suppose with some kind of microcontroller. Now let's talk about Isaac Lab. First of all, this is open source software, and you can find the source code, complete source code on the GitHub. But this software, it works on top of the Isaac Sim. And I have made a video about Isaac Sim. If you have not watched it, watch it afterwards. Isaac Sim is not open source, but Isaac Sim is free and you can use it with no problem. But you need quite powerful computer to run it. The documentation about Isaac Lab you can find on the GitHub page of the Isaac Lab. And over here we can see that Isaac Lab is a unified and modular framework for robot learning that aims to simplify common workflows in robotics research, such as reinforcement learning, this is exactly what we need, learning from demonstration and motion planning. Learning from demonstration is also should be interesting. It's built on NVIDIA Isaac Sim to leverage latest simulation capability for photorealistic scenes and fast and efficient simulation. Now let's look at the installation. To run the Isaac Lab, you basically need to run the Isaac Sim, and for Isaac Sim, you need quite powerful PC. I used the local installation because this is simplest to work with, but you can also run it on the cloud. And for the installation, it was super straightforward, like it's shown over here on this page. And first of all, I installed the Isaac Sim. So I used the Python environment with CUDA 12 on Linux. Afterwards, over here, we can verify that the Isaac Sim was properly installed. And after we can do the installation of the Isaac Lab. For the Isaac Lab, you need to install the Git. This is very simple. Afterwards, you can clone the Isaac Lab. You can install the dependencies, and you can install the Isaac Lab itself. So the installation is super straightforward. Just follow this page. And for me, it was like zero problem. To run the Isaac Lab, it's usually the commands like over here, where you run this one from the Isaac Lab directory, and you should be in your virtual environment, of course. And most of the time, the command looks exactly like this one, like over here. So you have the script, which is train.py or play.py, depending if you are training or you're looking at the already trained model, and you specify the task. When the installation is complete, I think it's a good idea to do tutorials. I went through some of them. I have not made all of them, but I think it's very useful. Also, I think it's important to know that if you have the question about specific commands, you can find quite a lot of explanation about these commands over here in the source API. There are many modules here, and they are explained not always in details, but you have some explanation. Let's talk about theory, how our reinforcement learning should work. First of all, we need a model, neural network model, and this model would decide which action robot should do. So at the output we have actions. So basically this model should say to our robot which joint it should rotate to which position. So the position for each joint. At the input we should have commands. Basically commands say to our robot should it go straight forward or backward, or should it turn. So this is a commands, let's say, from the joystick. But this is not enough to work for our neural net, because it does not know about the position of the robot, it does not know about the direction of the gravity, so it does not know anything. So it needs some information, and we call this information observations. So over here we will have the data from the actuators and from the IMU sensor in the real robot. But we are talking about simulation. So, and because we are talking about simulation, the actions goes not into the real robot, but it goes to the Isaac sim. So inside the Isaac sim, we should have the scene. And this scene should have all the components necessary to run this simulation. And basically this is robot itself, the terrain on which this robot is working, and also sensors. And in the Isaac sim it should also have the light. So this is our simulation. So when the simulation knows where it's going to rotate each joint of the robot, this simulation can predict the observations. But also this simulation can calculate rewards, and we need these rewards in order to update our policy neural net. Also for the simulation, it's really nice to have the randomization. We don't know exactly the masses of the links, we don't know exactly the friction inside the joints, we don't know exactly the friction between the feet and the ground. So we need to account in the simulation that we don't know precisely all the parameters. So how we do this? We randomize several parameters. And this is called, in the Isaac Lab, it's called events. Inside there is all the randomization. So it means that from time to time, it's going to change the friction parameters, it's going to change the masses of the links. And also over here, there is a command which is going to randomize the initial state of the robot. Another useful thing is curriculum. This is quite interesting thing, and what it does, it changes the parameters with the steps. For example, when we start to train the robot, and the robot don't know yet how to walk, what we do, we give the robot the simple terrain, the flat terrain. And also we can give him the commands with the really low speed. So we don't force the robot to go with a high speed. We start with the low speed. But afterwards, with additional steps, when the robot is already knows how to walk on the flat terrain, it knows how to walk with the slow motion, with the slow velocity. In this case, we can change these commands. So we can change the velocity, we can give the terrain more complicated to the robot, and all this is defined in the curriculum. Now let's quickly talk about different components. For the commands, it's quite simple. What we command the velocity in x direction, the velocity in y direction, and the angular velocity around z-axis. Z is pointed upward. So basically it means that the robot can walk in one direction and in another direction, and it can also rotate. So it's not just walking like this. It can also rotate. And for actions, it's super easy. The actions, it just gives the position for each joint. So these joint positions. For the observations, it's a little bit more tricky. There are many components here. So there is a linear velocity, angular velocity, direction of the gravity. This is basically the data from the IMU, current joint positions, joint velocities, and also we add here the last action. The last action which was applied to the robot. Over here in the Isaac sim, the terrain is simple, it's easy to understand, so it's just a different terrain. The flat one, the steps, the waves, sensors. Over here we can use mainly two types of the sensors. The height of the robot, so the distance between the base and the ground. And also we can use the force sensor when the robot puts the feet on the ground. But here we don't use these sensors. And in the robot, you need basically to specify the USD file, and also you need to explain each actuator. For the curriculum, usually what we can do, we can change the terrain level, push force, and also command velocity. The command velocity is chosen randomly, but the maximum command velocity is limited over here. And for the events, there are a lot of randomizations, like for example, robot materials for the friction, robot link masses, joint parameters, basically it's friction inside the joint, and inertia, external pushing forces. And over here there is a reset of the initial state of the robot. And the rewards is the main, most interesting part of all this scheme. First of all, we give the rewards if the actual velocity is close to the target velocity. So tracking Vx, Vy, and also we track the angular velocity around the axis. And we penalize the velocity in the z direction, linear velocity in the z direction, and we penalize the angular velocity in the x and y direction. Angular velocity and x and y, it means that the robot is about to fall. Also, there is a penalty for the fast changing of the torque, joint torque, and for the action rate, for the change in the action rate. We need this to increase the smoothness of the trajectory. And also, we would like that our feet stays in the air for some time, so feet air time. So this would prevent to make a small steps. And 8, feet slide. We don't want our robot to slide the feet on the ground. So these are the main rewards, but it's not all of them. Enough of the theory, let's look at the code. As I told you, the Berkeley Humanoid reinforcement learning part is open source. And here's the GitHub page of this Isaac Berkeley Humanoid. So these are the files to run with Isaac Lab. And first of all, the training is done with RSL-RL. I have no idea what is this, but I know that quadruped and biped robot, at least most of them, for the training they use this one. In order to use these files, you need to install them, but it's not the real installation, as you can see over here. And afterwards, you can run the training exactly the same way as any other training in the Isaac Lab. So basically, you need to use isaac-lab.ch with this script train.py, and afterwards you need to specify the task. And when the training is done, you can play this training with a similar command over here. So let's look at the files. First of all, over here there is these two files, play.py and train.py. This is not super interesting because these files are copy-paste files from the Isaac Lab, and I can even show you them over here. So this is the source code of the Isaac Lab, and if we go to the scripts, over here we have reinforcement learning, RSL-RL, and you have these files. Everything is interesting over here, actually even over here. What we have here? We have here the model for the actuators, the assets, this is basically our robot over here, the task, this is the main part where there is all the rewards, events, curriculum, etc., etc. terrains. This is just basically the terrain on which this robot trains. There is an actuator folder over here because the Berkeley, they use quite a special model for the actuator. Assets are more interesting. There is description of the robot in the Berkeley Humanoid.py, and there is USD file over here. And if we look at the Berkeley Humanoid.py, we see that basically there is a description of the actuator over here, of each actuator, and over here is the robot itself. So this is the USD file, initial state of all joints, and the actuators. And also there is a soft joint pose limit. The soft joint limit is at 95% of the real physical limit of the actuator. And this is necessary for the rewards, because in the rewards we ask our robot not to go beyond this value. So now we know what is actuators, we know what is assets. Now let's look at the terrains. This is also straightforward. Over here there is a terrain configurator, and this terrain is used in the tasks. And over here we have other parameters of the robot, like we have the terrain, where we use the terrain configurator, which we saw previously. There is also robot, which is going to be initialized in another file. Sensors, light. This is a command, but basically the command is just a uniform velocity command. Linear velocity in x direction, linear velocity in y direction, and angular velocity around z-axis. The actions is just joint positions. And so the observation is linear velocity, angular velocity. And the interesting is that on this observation we add a little bit of noise. So like this robot does not know precise value, it knows the values with the noise. The projected gravity, so basically this is going to be IMU data. The commanded velocity, so the target velocity over here. Hip position, knee position, feet position, another feet position with different noise on this position. Joint velocity, last action. And afterwards there is a randomization, but this randomization is basically events. First, the physical material, and there is a randomization in the friction, randomization on the link masses, randomization on the base masses, randomization on the joint armature. Joint armature is basically moment of inertia of the rotor part of the actuator. Randomization on the joint position, on the joint friction, on external forces. Over here there is a rewards. The reward for tracking linear and angular velocity. The penalties for the linear velocity in z direction, for the angular velocity in x and y direction, for the excessive joint torque changes, for the fast action rate changes. We also want to have our feet air time is not very small, and we don't want to have the feet to slide. We also don't want our robot use these joints too much, and also we don't want our robot to use knee too much, and this is needed in order not to work on the bended knee, I think. I'm not specialist in all of this. The termination. So the simulation is terminated when there is either timeout or when the robot falls. Curriculum on the terrain level, on the push force level, and on the command velocity. And over here, we assemble everything together. And by the way, it seems very complicated, but the similar examples you can find in the Isaac Lab. Let me show you. If you go to the Isaac Lab over here, you can go to the source. Over here there is assets and also tasks. Let's go to the task. This is the most interesting. Tasks. Manager based. We need locomotion, velocity. This one. So this is kind of default values for the default robot. And over here there is a scene with the terrain, with the robot, with the sensors, and with the light, as before. There is a command, action, observations, linear velocity, angular velocity, projected gravity. So this is also exactly the same as in previous Berkeley file. Now over here it's event, but it's the same as randomization in the previous file. The rewards and very similar termination with a timeout and with the detection when the robot fall. Over here curriculum is a simpler one, it only has the terrain levels. Again, everything is assembled over here. And so this is kind of a generic file. And for each robot, there is a small modifications, sometimes small, sometimes less small. Like for example, if we took the robot Cisse, it's also bipedal robot, and it also has 5 degrees of freedom per leg, as we would like to build. So this means that this example is relevant to us. And over here there is some additional rewards, and it's based on the rewards from the previous file velocity and CFG, this one. So as you can see, it's basically the same things which we discussed before, but they're written in the code. And what I did, I took the files from the Berkeley and I modified them in the way to be more similar to the newest examples. So the Berkeley was written for the Isaac Lab version 1.0 and Isaac Sim 4.0, and I rewrote it for the Isaac Lab version, I think it's 2.0, maybe I'm wrong, and with the Isaac Sim 4.5. There are some modifications and I made these modifications. And so I have a new file, which is over here. So like this, I assemble everything together. So there is a terrain configurator. Over here, there is observations. This is the events with all randomization. This is the rewards. This is curriculum, termination, and everything assembled together. And so this is a file which describes our robot. So there is a link over here to the USD file and the initial position and all the actuators over here. And by the way, USD file I created from URDF file. Let me show you the URDF file. This is a fit, this is a hip, adduction, abduction, this is a hip flexion extension, this is a hip rotation, this is a knee, and the same for another leg. When we have URDF, we can use the Isaac Sim in order to create the USD. And so I run the simulation for the Berkeley humanoid robot, for the Cisse robot, and also for our bipedal robot. And by the way, here's the commands to run this simulation. And you can add different flags for this command. For example, if you add headless, in this case, you would not have the visualization during the simulation, but simulation is going to be faster. And after around 13 hours of the simulation on my RTX 4080, the robot was perfectly capable to walk. And by the way, the blue arrow and green arrow on top of the robot is target velocity and actual velocity. After this simulation, I also tried the simulation of the Cisse robot. And it was working, and actually it started to work after 1 hour of the simulation. But quite quickly the robot learned to keep the feet in the air as long as possible, because the robot was getting more rewards when it keeps these feet longer in the air. There is no this problem with the Berkeley robot, because the rewards was a little bit more intelligent, and if the robot was keeping feet in the air for a long time, it was not getting any additional reward. So the Berkeley robot has the cap on the maximum reward for the feet air time. And over here we can see the result of the training of our bipedal robot. It works not bad for the first simulation, but I think over here we can still tune a little bit the rewards. So probably there is a room for improvements here. And by the way, with this command you can visualize the trained policy. By default it shows you the last trained policy, but if you want to show the result of specific training, you can specify it in the checkpoint flag, like over here. Another interesting feature of the Isaac Lab, that in the training command you can add flag video, and like this the simulation is going to save a small video every certain number of steps of the training. And so afterwards you will have a lot of different videos, very short, small videos like this one. And thanks to this video you can see how the training was progressing. And I think in our case it was quite interesting. So at the beginning the robot was not able to stand. It was falling every time. After some time it started to fall less frequently, and at some point the robot learned that it can sit, and when it's sitting it's not falling. And at the beginning, I thought that this is going to be the problem, that the robot is going to sit till the end of the simulation, but no. When it was sitting, it started to walk a little bit, and afterwards, with the time, it got up and it started to walk. For me, this was really interesting, and I'm really happy that it's working. It's not yet working perfectly, but I think it's enough to try to implement this model inside the real robot. And afterwards, probably we're going to tune this model in order to make this working more natural, better looking, more robust. Thank you for watching this video till the end. Today we have learned how to teach our robot to walk, at least inside the simulation, inside the Isaac Lab simulation. And the next time we are going to build this robot and to try to put this simulation into the real robot and see how it's going to work. And in order not to miss this video, don't forget to subscribe to my channel. And also I would really appreciate if you put the like to this video, to put the comment, share this video, etc, etc, etc. And also I would like to say a huge thank you to people who support my channel via Patreon and YouTube channel membership. Here are their names. Thank you, you are the best. As usual, stay safe, good luck with your projects, and see you next time.